So welcome to lecture 4 of EI-207 Digital Electronics. In this lecture we will start our unit 2, and this unit is particularly about combinational circuits. So in this unit, first we will understand what are combinational circuits, and then later we will discuss that what are the general steps or the procedure to design any combinational circuits. Later on we will understand the method with certain examples. So the examples are more important in this particular unit. So the examples which we are going to discuss, and we are going to design various circuits in this particular unit, and this all circuits will be the combinational circuits only. So the circuits which we are going to discuss in these units are adders and subtractors, various types of adders and subtractors, half and full adders, subtractors, parallel adder subtractors, and then in the later unit in the later part we will discuss the modified adders. So whatever problem we are going to face in this particular sort of adders, so how to improve on that. Okay, so some of the improvement will be seen in this particular adder subtractor, and then parallel adder, and then later on we will see some more modifications in this modified adders. So then we will see what we have already learned in our last unit, that is the BCD numbers. So we will see that how to perform how to implement the hardware circuit to perform that BCD addition. So we have already learned that how to perform BCD addition. So here we will design a circuit which will perform addition of two BCD numbers. Then we will see further again whatever we have learned in our last unit, that is the code conversion. So again we will here discuss the hardware circuits to design this code converters. Then there will be magnitude comparators, single and multiple bit magnitude comparators, and then there are other circuits, decoders, encoders, multiplexers and demultiplexers. So these are the topics these are the objectives which we are going to discuss. These are the things which we are going to discuss in this particular this lecture. So I'll take various parts of this lecture, but probably in the first part we are going to discuss about the adders. Okay, and that too is half and full adders and subtractors completely. And this adders, because I am trying to discuss it today itself, because you may require that in your lab class also. So it's better to go it as soon as possible, to cover these things as soon as possible, because you have to realize this through the experiments also. So let's start with the combinational circuits. So if I talk about the combinational circuits, so basically in digital electronics, any circuit can be divided into two types. Okay, so there are basically two types of circuits in digital electronics. First type of circuits are called combinational circuits, whereas the other type of circuits are called the sequential circuits. So we will not discuss sequential circuits here, but those sequential circuits we will discuss in the next unit. But if you talk about the combinational circuits, then the combinational circuits are the circuits whose output depends only upon the present inputs. Okay, so whatever input you apply, the output will be dependent upon those inputs which are applied at this moment. Okay, not on the past inputs. So this type of circuits whose output depends only upon the present inputs are called the combinational circuits. Okay, so there can be different inputs. Let's say in this particular block diagram, if we see, so there are various inputs, so n inputs may be there, so the number of outputs then may be different than this n input variables. So there may be n input variables and there may be m output variables. So what is the method to design any combinational circuit? So basically we have to design this black box. We have to find that how the gates will be connected inside this black box. Okay, so because this black box will have certain inputs and certain outputs will also come from this black box. Okay, but our aim, whenever we say we have to design something, okay, so we have to design something inside this black box, so whatever is there. So let's see. to find out that which gates are used and which gates will be used in a particular combinational circuit, and in which fashion they are connected. So to do that, we have to follow certain procedure. So that procedure is not difficult to follow, and we will learn this procedure with the help of various examples which we are going to do in this particular unit. But if you just consider what is the theme of this unit and the general procedure, so this is the general design procedure for any combinational circuit. So first of all, whatever is being told to you, okay, so verbal statement will be given. So from that verbal statement, or whatever definition you know, because some problem, I mean something if you talk about, let's say if I talk about adder or addition, so you know that what does addition means. So first of all, I'm telling you addition, so I'm not telling you any mathematical thing, but I'm just telling you some word, and based on that word you know that what mathematical operations you have to do. So similarly, whenever you come across a new word, first of all you have to find that what does it that word means. So what is the basic definition for that word. So once you know the basic definition of that word from the verbal statement which has been told to you, you have to get the logic diagram. Okay, the diagram in which there will be various gates, various gates will be connected. Okay, so that diagram, that particular circuit, that particular definition will be implemented with the help of that some gates. Okay, so so this is what the aim is. So from the verbal statement we have to reach to the hardware. So let's say from the verbal statement, from the whatever is being said to you, you find that how many number of inputs will be required and what will be the corresponding number of outputs for that particular black box will be. So from that definition in itself, you find that how many number of inputs will be required to realize that particular definition or that particular operation, and what will be the various outputs as well. So that is what we find from this statement. Then once we are able to find the inputs and outputs, number of inputs and outputs, then we try to find the relationship between the input and output. Okay, that relationship is written in the form of a truth table. Okay, so that truth table is nothing but the same which we have learned in our last unit. So that type of truth table we have to write. Okay, so truth table is a relationship, I mean which the table which shows the relationship between the input and the output. So it on the input side it shows all the possible combinations of the input variables, whereas on the output side it shows the presence or absence of a particular combination. So that is what the truth table. So you have to write all the possible combinations of inputs and get the output. So when the output is present, so we have to write a truth table. So once the truth table is written, then by using the simplifying techniques, so usually you can use any of the three methods which we have discussed in the last unit. So either you can use Boolean algebra, you can use K-map to get the simplified form from the truth table, and you can also take the tabular method. Okay, but usually we are going to, I mean in most of the examples you will see that we are going to use K-map for our simplification. Okay, so that is why you should be very much comfortable with K-map simplification, that what are the K-map rules and how to apply those K-map rules to obtain a simplified expression, okay, from the mean terms or whatever terms, standard form or canonical form, in whichever form the question is being given to you, you should be able to find the answer in the simplified form. Okay, now one more thing which I should specify here itself, that whenever there are multiple outputs, so we have to write the K-map for each of the output. Okay, it is not like we will write the output for only just one of the output. We have to write the K-map for every output, and then we have to simplify them. Okay, simplify them separately, and then with the help of the whatever inputs are available, we make a combined circuit. Okay, in which all the inputs, all the outputs will be realized simultaneously. Okay, so this is what we have to do. So once we have done this, then simplified expression we get. Once we get that simplified expression, then we realize that expression with the help of either our and or NOT gates, either in the sum of product form or in the POS form, product of sum form. That depends upon what we want, and that also depends upon the hardware. So I mean, which expression will give you the which particular expression will require least number of gates. So depending upon that, the particular expression which require least number of gates, we will implement that circuit. But though we will not go into that, but still, I mean, you can try that from the book as well, but we will realize both the type of circuits. Okay, it means the expression, SOP expression, as well as the PO expression, POS expression. In some of the questions you will see both type of expressions, and then later on we can implement the same thing with the help of our universal gates, NAND and NOR gates as well, so as been required. So, and then we see that whichever expression gives us the implementation with least number of gates, that is our real minimum. Okay, real minimum expression. So real minimum hardware, to get the real minimum hardware expression, we have to check all the possible combinations. Okay, that which one is like will give this particular thing what we want. But here in this when we will learn with the things with the examples, we will implement the things with the basic gates, then with the help of NAND gates, and then with the help of NOR gates as well. And in some of these circuits we will also require the derived gates like the XOR and XNOR gates, so we'll use them as well. Okay, so let's start with the adders. So this was the whatever we have learned in this particular slide. So this is the gist of this particular lecture. So repeatedly we are going to use these steps. Okay, so this is the theme, and I mean, if you learn this particular thing in the next up till the end of this unit, we are continuously going to apply these steps to get the reduced expression from the logical statement, from the verbal statement, whichever is given to us. Okay, so this is what the procedure which we have to follow. So now let's start with the adders. So adders, if I talk about, so basically in digital electronics, if we talk about, so we talk about two adders, so half adder and full adder. So when we talk about the half adders, it is nothing but a circuit which performs addition of 2 bits. So adder is like addition. Okay, and if the circuit performs the addition of 2 bits only, then that circuit is called a half adder. Okay, it may have carry, okay, but sometimes it may not, it may also not have carry, so no need to mind it. So let's say, and then we will discuss the full adder. So let's start with half adder and then we will come to the full adder. So half adder is is a function, is a boolean function which adds two bits only. So let's say two variables are a and b. So this is what we have to do, and then we will find its truth table, then simplify it with the help of k-map. Then whatever function we will get in SOP or POS form, we will implement it with the help of basic gates, derived gates, NAND gates and NOR gates. Okay, so this is what we are going to do. So half adder is, again I have told you that this is a plus b we want to do. So if suppose we have to perform the addition of 2 bits, so then if you write the truth table for those 2 bits, so then it will look something like this. So this is the input side. So in the input side we have written the 2 variables a and b. Now in the output side, if suppose we perform the addition of these 2 bits, and first of all what we have to do is we have to write all the possible combinations of these inputs. So all the possible combinations of these 2 variables will be like this, starting from 0 0 to 1 1. Okay, so these are all the possible combinations of 2 variables. So we have written all the possible combinations of 2 variables. Now once we have done this, then depending upon the function, whatever functionality this specifies, so we have to write the outputs. So output in this case, as it is an addition operation, so it will generate some and let's say some carry forward will also be generated. So the output will have 2 bits. Okay, so 2 bits will be, or 2 variables should be there. So I have written them as sum and carry. You could write it as s and c as well, or x and y as well. So it is your choice. Okay, so sum and carry. So let's say if I add 2 numbers 0 0, so then what will be the possibility? Sum will be 0 and there will be no carry. So I have written that here. Okay, if I add in the other case 2 variables whose values are 0 and 1. okay. So then the sum will be 1, okay. There will be some sum, but no carry forward will be generated. So that is written like this. Again 1 0, so same 0 1, no carry, sum will be 1. But if I make both the variables 1 1, okay, so then in that case output will be what, sum 1 0, isn't it? So 1 is carry forward, so carry is generated in this case, and the sum bit is 0. So you see, this is what I was telling when I was telling you that we have to write as many number of outputs as are possible. So we have to write the truth table. So first we have written the truth table. In this truth table we have written the input combinations, all the possible combinations of the input combinations, and then we have marked the terms for which this particular outputs will be 1. Okay, so this is what we have done so far. Now from this truth table, if suppose we have to we need to find, we have to find this the minimum expression for sum and carry, the hardware implementation. So we want the hardware implementation for this, and for that we have to require some boolean expression that we will realize with the help of our gates. So to get the expression in the simplified form, we have to use the K-map method. Okay, this is a simple problem and you will understand that very simply here with the help of this 2 variable K-map. But later on, again, if it becomes a little bit 4 variable expression or 5 variable expression, still the procedure will be same, but you may require some more techniques, some more better techniques to simplify this. Okay, if you know your this techniques very well, then no need to worry about whatever number of variables you get. Okay, so sum. So let's say I have to, as I have told you that for each of the output we have to apply the K-map. So K-map technique will be applied for each of them, for each of the output. So our outputs are sum and carry. So we have formed this truth table, K-map for sum variable and then for the carry variable as well. So for sum variable, if I make the K-map, so then I will fill up the entries. So you see, these are the places for your input variables. So this is 0, 1 and then 2 and 3. Okay, so 0, 1, 2, 3. So these are the places. So you can see from this table sum. So wherever this sum is coming as 0, so this is 0, then 1, this one, then 1, this one, and then this 0. I have filled it here 0. Then if I try to following the rules, if I try to form the pairs or any groups, so I can see that I cannot form a quad. So okay, because there are 2 zeros, all are not 1. So then what we have to do is we will try to find the pair, and still we can see that no 2 cells are adjacent here. So then we cannot the ones are not filling the adjacent cells, so we cannot form the pair as well. So then if we write that these terms separately, so then the sum expressions we find that it is like A complement B plus AB complement, okay, which is nothing but an XOR gate. Okay, so this sum expression, this whatever we are getting as a sum, can be implemented with the help of an XOR gate or by this expression. Okay, so there are 2 possibilities. So this is, if we implement it with the help of this, then we call it a derived gate implementation, and if we implement it with the help of this expression, then we call it the basic gate implementation. Okay, similarly we fill up the entries in the carry map. Okay, so carry is the other output, so we have drawn the K map for the other output as well. So carry is the other output, and we can see that the output is becoming 1 for this particular combination when both the inputs are 1. So this particular combination is this one. Okay, so this cell is the cell which where both the inputs are 1 1. So this and this one, both the inputs are 1. So we have filled the 1 here, and there is no other one, so it cannot form a pair with any other one. So it is separate. It is separate in itself. So this term will come by as it is. So it is A dot B. So we can write it A dot B. So carry expression, if we simplify, so this expressions are written in the simplified form. Okay, here. Now once we get this, so whatever black box we have seen, so that black box earlier is like becoming like this now. Okay, so now this is a single bit half adder, or a half adder is this. This is the half adder, and then 2 variables I have taken, so A and B, and 2 outputs are there, so sum and carry. In the previous block diagram I have shown you the general general where there was n inputs and m outputs. So here we can see that in this case n and m both are equal. Sometimes at some places you may see that they are not equal. Okay, so they may be equal, they may not be equal. Number of inputs may be equal to the number of outputs, or they may not be equal. Okay, now these expressions we have got, that these expressions are this. Now inside this function, inside this black box, we have to do something so that at this output, at this terminal, we get this expression. Okay, and at this terminal we should get this expression. To do this, we know from our basic previous unit that how we can do this. So there are two possibilities. Let me explain you with the simpler one. Both of them are simple one. So let's say if I take the sum, this basic expression a complement b plus a dot b complement, and the other expression. So you see, if I take them simultaneously and if I try to implement with the help of AND OR gates, so you can see a here and then a naught. If you use a NOT gate here, so a naught you will get a bar, then this is b. Okay, so this is b, so we are taking this from b, so b, so a bar b, so we are getting here as a bar b. Similarly from here we will get a, so this is the other input a and this is the another input, so b. Okay, so a b bar, so a b bar we are getting a bar b and a b bar, and now we have ORed them up. So here we get a bar b plus a b bar, or a XOR b, right? Similarly, if we see a dot b, so we have taken the input from here a and the other input from the other this b. So then our b is this, sorry. So we have taken this. So this is our b input. Okay. So a and b, if we take them simultaneously, then we can see that we have applied this a dot b, right? Okay. So a dot b. So your a dot b is nothing but this carry. Okay, so this is your carry expression a dot b. So this is how we can implement the expression with the help of our basic gates. Now with the help of derived gates, if you want to implement, then you can instead of using all these AND OR gates, AND OR NOT gates, you can directly use a XOR gate also. So the same circuit, the same expression can be implemented with the help of, here we implemented with the help of XOR gate and an AND gate. So XOR gate shown like this. So it is, if the inputs are A and B, so output will be A XOR B, and the carry output will be this. So you see this input, what is inside the black box. So this would have been inside the black box. Okay. So by solving the expressions, by writing the truth table and then simplifying it and writing the expression in the simplified form by using the K-map method, we have implemented the circuit with the help of our gates, basic gates and the derived gates. Now let's try to implement the same circuit with the help of our universal gates. So the method is simple, and I'll explain it in full detail for this particular adder, because this is the first circuit which we are implementing. But later on, I think you should try it by your own. Okay. So I will although show you the circuit, but I won't tell you the things in detail. If you want them, you can refer from the book or you try to solve the circuit by your own. Okay. So you see what we'll do here to implement, to get the NAND logic implementation is, we have taken the sum expression and we rewrite it in such a form using our Boolean identities in such a form that we get the expression for NAND circuit. Okay. So this is what our aim is. So how we do it? Let's say this is our basic expression for sum. Then here whichever terms are missing, so you see a bar and b bar are missing. So this is the general technique which we do. Okay, so whichever variables are missing, we add them up. Okay, so product of this. So we have added them up here, and then by taking this common from this particular term, this particular groups, then if we take this common, so we get the expression something like this. Okay, this expression further if rewritten in a different form, so it becomes this expression. Okay, so a dot a b complement and the whole complement of this plus whole complement of b dot a dot b complement. Okay, and this complement. So if you read this expression properly, and you see now whenever we have to implement the circuit with the help of NAND gate, then we should have this whole complement. Okay, whole complement and this expression in the form of again this a dot b and means x dot y sort of. Okay, so x dot y whole bar we want. Okay, so x dot y whole bar, if we get this type of expression, then it can be easily implemented with the help of NAND gates. And if we want the expression for NOR gate, then it is exactly opposite. So then we will require something like x plus y whole bar. So for this case, if we implement this expression, okay, so this we have done, this we got with the help of our Boolean identities simplification method. And then we have implemented with the help of this particular circuit, whatever we have written, with the help of NAND gates. Okay, and you can also use our this basic technique to convert this given circuit. This, let's say this is your circuit, so you can put two this bubbles, okay, here, and if you put one bubble here and the other bubble at the input of the OR gate, again you are going to find the same circuit. So let me show you that this is our previously OR gate. So the bubbled input bubbled OR gate becomes our NAND gate. So bubbled OR is becoming your NAND gate, and this was earlier your AND gate, and you have used a bubble here, so it becomes a NAND gate. And this is again being there, you have used some technique, some proper method to simplify it. Okay, you could have used the NAND gates as an inverter, but then the number of gates will be more to implement, the number of gates required to implement the circuit will be more. That is why just by simplifying it properly and writing it to the expression properly, we have simplified it like this. Okay, so this is what your function, this is how your circuit will look like for NAND gate implementation. So half adder with the help of NAND gates looks something like this. Okay, now from this you can see that as this is your input A dot B bar. Okay, so A dot B whole bar you are getting, so A dot B whole bar, and then if you do the complement, if you use again an and again this inverter here, then you will get A dot B double complement. Okay, A dot B complement is available here, and again its complement, so it is A dot B you are getting here. So this is what the expression you are getting. Okay, similarly if you rewrite the same expression in different form, so it is like how we want to implement it. So depending upon how we want to implement it, we can rewrite the same expression in different forms. So again we have taken the same example, okay, same thing, same expression written in the same form, then but now in this case we have taken something else common. Okay, so now you see in this expression we have taken something else common. Rather than making the term as A dot B, we have simplified it in terms of A plus B bar. Okay, so A plus B bar and A plus B. If we write it in such a form, then we get it is possible for us to implement it with NOR gates. Okay, so this is the expression which we require for NOR gate implementation. So if we implement this here, then you can see that A is available here. So A complement, okay, so A complement we are getting from here, and here we are getting B complement, and here we are getting this term A plus B complement. So this term we have taken, and we have taken this complements. Okay, this A complement plus B complement, and then we have like again OR them together for this expression. So you get this particular expression, right? So this is what it is. And similarly for carry expression, if you see, so A dot B, if you use the De Morgan's after double complementing it, you can see that it can be written as A bar plus B bar also. So the expression is this, and this output is available here. Okay, so this is how we can implement any circuit with the help of NAND and NOR also. Not only with the help of derived gates, basic gates, but we can implement the circuit with the help of NAND and NOR gates also. And this is important to remember, okay, because you see whatever we have done for half adder will be used to implement the full adders also. So you just remember that to implement a half adder, this is what the circuit we have implemented. So we required 4 AND gates. So you see in this they are connected in such a fashion. So you should remember this. Okay, and the NOR gates are connected in this fashion to implement your this sum and carry expression. Okay, so this same circuit we will use later on repeatedly to implement our full adders and full subtractors also. Okay, so you see now let's see the full adder. So this was all about the half adder. Now let's say the full adder. So full adder is nothing but a circuit which performs the addition of 3 variables, okay, or 3 bits I should say. So the previous circuit half adder was nothing but addition of 2 bits a plus b. Now we have added one more variable to it, or one more bit to it. Okay, so this is our C. So we will again do the same procedure. We will write its truth table, then we will simplify each of the output with the help of K-map, then we will write the function in the SOP and POS form, and then we will implement it with the help of various gates. Okay, so now you know that what is the definition for your full adder. In fact, you can pause the video and can try the implementation by your own also. So I'll tell you the definition in a single line, and then you can use that definition, and in fact you know that definition as well. And by that definition, whatever I'm going to tell you, you can try the implementation by your own. Okay, but if you are not able to find it, then you see the video, and later on, if it's not possible for you to implement this, still if it is not clear to you that how to implement how to follow the procedure, then you learn it from the next example, okay, with the help of this full adder example, and then try it for the next circuit, because the procedure is going to remain same. We are going to follow the same procedure to implement any circuit, okay, whichever circuit we are going to study in this particular unit, we will follow the same procedure, right? Okay, so you see, for this full adder, to implement this full adder, what we will do is we will write its truth table. So truth table, how we will write? First of all, we will determine the number of inputs and outputs. So in case of adder, as you know, we have already told you that there are 3 variables. The variables are A, B and C. Okay, in the previous slide I have written C, but you can write it as carry input, because this is the variable which can take the carry also. Okay, and so carry input. So these are the variables on the input side, and you can name them anything, A, B, C, A, B, D, or whatever you like. Okay, so I have named them as A, B, C. And if you add 3 bits, then again the outputs will have 2. I mean, there can be 2 outputs. So it have 2 bits at the output. So they are some bit, it have some bit and the carry bit. Okay, so carry output will also be generated. Carry will also be generated. Okay, so let's say these are the inputs and outputs we have. So if we write the truth table for this circuit, then how the truth table will look like? So you see, if there are 3 variables on the input side, then you know that the 3 variables can have 8 possible combinations. So we have written all the 8 possible combinations here on the input side, starting from the 0 0 to up to the 1 1. All the combinations are written here. Okay, you just check it if anything is missing. So that may be my fault. That is my fault. Okay, there should not be anything should be missing. Okay, so all the combinations, all the 8 combinations I have written. Then following the same rule that of addition. So if 3 zeros are added together, then you see sum and carry both are 0, right? If only one input is 1, then you can see that the sum bit is 1, whereas carry bit is 1. So for this case and particularly this case, so there is only sum bit is becoming 1 and carry bit is 0. Whereas in the cases when the two input variables are becoming 1, so the sum will be 0 and carry will be 1. Okay, so carry is 1, sum is 0. So you can see this. Similarly, you can find this for this particular thing. Okay, so 1 0 1. So again, 2 number of ones, 2 input variables are 1. So your output will be sum 0 and carry 1. Same as what we got for our half adder. The only change is this particular input. So when all the input becomes 1. Okay, so this is the new combination for this circuit. So you see, in this case, sum and carry both will be 1. Okay, so if both of them are, if all the inputs are 1, then your output will also be 1. Okay, so now when you have defined this, then you know that your output will be, the block diagram of the output will be something like this. It will have some black box, and that black box will have 3 inputs and 2 outputs, and the functionality of those will be defined by this truth table. Now taking this truth table, what we do is we write the K-map for them. Okay, so we write the K-map for each of the output. So this is the K-map for Cout variable, and this is the output, this is the K-map for your sum variable. Okay, so we have to write them separately. There is no other choice. So once we write them separately, then we fill up the entries based on this truth table. So you can see that this is particularly the square for the cell for 0 0 0. this is the cell for 001. So 0001, then you can see it is 2, then 3, 4, 5, 6, 7. Okay, so now if you see, then you can fill up the entries here accordingly in the carry output. So carry output is becoming 1 for this particular cases. So it is becoming 1 for 3, then 5, then 6 and 7. So you see 3, 5, okay, no sorry, 3, then 0, 1, 2, 3, then 4, 5 and 6, 7. So 5, 6, 7 and 3. Okay, so it is becoming 1 for this cases, you can see. Okay, you can check it. And similarly you can see that your carry output is becoming 1 for which cases? It is becoming 1 for 1, 2, okay, 1, 2 and 4 and this 7. So you see this 1, okay, 0, 1, then 2, okay, then 4, then 7, right? So this is how you fill them up. After filling them up, we following the rules of pairing and following the rules of grouping, we form the pairs or the quads as possible. So in this case only pairs are possible, so we have formed the pairs and then have written the expression in this form. So you can see that in this particular expression I have written them the terms separately, okay, just to simplify it, or like just to implement the circuit with the help of these gates as well, or rather you can implement it with this is for carry output and this is for the sum output, okay, expression. You can implement the same expression, because if you want to implement the expression with the help of our basic gates, then we will require this expression for sum, okay. Carry is like no problem, but for sum we will require this. If you will just use the simplification technique, then you will get this XOR gates, and then XOR gates are not the basic gates. That is why we are not used this expression and have written the expression in this form also. But this is like the at the very first time I will tell you the expression, implement the expression with the help of this gates, but later on for further implementations we will use this expression, okay, of XOR. So this expression is more important, but just to realize the circuit with the help of basic gates, we have written this expression also, okay. So this is your expression for sum and carry. Now once you got this expression, then you can implement it with the help of your basic gates. So as the circuit was little big, I have shown them separately, but this is your sum and your this carry circuit, and you can assume that this input variables are connected with each other. So if this is A, you can assume that they are internally connected, although they are looking separate, but they are connected together, okay. And similarly this is B and this is B, so they are connected, okay. So what we do here is we implement them. So we take these expressions. So we have taken this sum expression and this carry expression in the form of basic gates, and we implement it, okay. So this is our expression, this is our implementation for our sum and carry output with the help of basic gates. You can check it, verify it. So let's say if I take this term A bar B C in bar, so this is implemented with the help of this AND gate, a 3 input AND gate, okay, and this comes together. And this OR gate should have 4 terms, so it is having 4 terms. You can check any other with this term randomly. So this is 3 variables A, B, C in, and here if you check this, so it should have 3 inputs. This OR gate should have 3 inputs, so they are coming 1, 2 and 3, and this input is A dot B, so no problem, B C in, no problem, then C in A, okay. So you see, this is what we have done. Depending upon whatever expression we have realized it with the help of our basic gates. Now the same circuit we can implement with the help of half adders and some other circuit, okay. So half adders and OR gate is basically required to implement our this circuits, okay. So this circuit also, so we can implement the full adder with the help of half adders and OR gate. So how we can implement it, we'll understand it here, and then later on we will see that how we can implement the same circuit with the help of NAND and NOR gates. So you see, and this is why I have told you that you should remember how we've implemented our half adder, okay. So you see the black box implementation for your half adder looks something like this. So 2 inputs were there and 2 outputs were there. So half adder have, let's say, 2 inputs A, B, and the output as C and S, okay. Earlier we have used carry and sum, but here being this less space, we are writing them as C and S. So C. So inside it whatever is there, it is going to generate this C, and that expression will be A dot B, right? Similarly here, the expression which will be implemented for sum will be A XOR B. Okay. Now what we do is, whatever outputs we are getting, we are feeding it to the another half adder. Then after feeding it to the another half adder, we see that, because you see we have to implement this expression and this expression. So we are trying to implement it with the help of half adders and some other gate, some OR gate. So this is what we are doing. So you see here, if we implement this particular, okay, and XOR it with this scene, then you see again we are going to get this this particular sum, A XOR B XOR scene, okay, because this input, which is though it is written here A, but it will be A plus B. So this is the input to this input will be A plus B, okay, A XOR B, and the other input is to the half adder is scene. So together they are becoming as, let's say this is your variable, if I write it as x is equal to A XOR B, so it is becoming x XOR scene, okay. So you see x was equal to A XOR B, so that is what is coming. So this function gives you that, particularly if you connect the half adders in such a fashion, and if you connect the output of the sum output of first half adder to one of the output of your second half adder, and then take the other output, I mean the output of the second half adder, then you get the sum as of, I mean the sum expression for the full adder. And similarly you can see that the other input as seen here, and this will become then because this input is x and it is A XOR B. So you see that both of them are ANDed together for this output. So it is becoming scene dot A XOR B. Now if this output we are getting from the second half adder, then these two outputs we are getting from the second half adder, then this output can be directly used as the sum expression, because this is what we have to implement. This is our sum expression, so this is what we have to implement, no problem. But this is not our carry expression, okay. So then what we do is, with some manipulation, if we see, so then if we input this to A dot B, this output of this first half adder and the carry output of the second half adder, and XOR them together, and if you simplify them, then we can see that the expression which we are going to get is this, and this is nothing but it is same as this. Why it is same as this? You can easily verify it, because you see these expressions, these two terms, if we take together, then you can see that if I take C in common from here, then it will become A XOR B, okay, plus means A XOR B dot C. So this will become something like this. So this is what we are getting. Okay, now from this, if I take AB common, then it will become scene plus scene bar, and scene plus scene bar, as you know, it will be what? 0. Okay, it will be 1. Scene plus scene bar will be 1. So the expression will be A dot B. So overall the expression will become A XOR B dot Cn plus A and B. Okay, so you see this is what the expression we are getting. This is the same expression which we got in our previous slide, and we have implemented it with the help of basic gates. So the same expression we can rewrite it in different form, and being rewritten in a different form, it becomes something like this. So we can take this output as well as this output and the carry output of the two half adders, and combine them with the help of our OR gate, okay, 2 input OR gate. So we get the carry output function. So this is the method to implement a half adder with the help of this is the method to implement a full adder with the help of 2 half adders and OR gate, right? Now inside this, I have already told you that there will be some XOR gate and some AND gate. So this is our first half adder and this is our second half adder. So whatever was written earlier is again repeated here, but it shows that this is your first half adder and this is your second half adder, and these are the inputs which are coming, okay. So although they were written horizontally, but here it is written vertically, so it doesn't make much difference, okay, any difference. Now let's implement the same circuit with the help of your NAND gates and NOR gates. So if you have to implement the circuit with the help of NAND gates, so then you recall it from your previous implementation of half adder, that if you implement the combination of this 4 gates, then you get here A XOR B. Okay, so I will not explain everything in detail because to realize, and because this four gates are, if are connected together, we get a XOR gate. Okay, if the 4 NAND gates are connected in such a fashion, we get a XOR gate. Okay, the output will be XOR. Now if this is ANDed with, sorry, if this is like in the to this NAND gate, if we put this as the one of the input and the Cin as the second input, then again it is becoming a second half adder. Okay, so the output for this will be your sum output. You can verify it very easily. So this particular half adder is repeated here also. Okay, so this four gates are repeated in here, same as it is. Okay, now and if you do this, then you know from your previous realization of the previous slide that the output of this 2 XOR gates connected back to back gives you this output. So this is your sum output. Then your carry output, to get the carry output, again there is a little trick. So the trick has been used as, this is the carry input here, the Cin is coming here. Then we take the inputs of the input to this gates are the output of this gate and the output of this gate. Okay, so this is what we have taken, and if we connect them together, you can verify it. You will get here A dot B whole bar, and here you will get A XOR B dot Cin whole bar. Okay, so this, if you will see this by the help of, if you will simplify it with the help of your De Morgan's, then you will see that the expression is something like this. Okay, so it is De Morgan's you have to apply. Then you can see that the expression you are getting as this, and this is the same expression which we have seen in our last slide, right? So this is how we realize our full adder with the help of our NAND gates. Now let's realize the full adder using NOR gates. So again, repeat, it is same as what we have seen. So you see, this is the combination of 4 gates, and here, okay, so these are the first 1 2 3 4 gates. So here we get this expression. Okay, probably I made a mistake here, so the input should be, okay, yes, no problem. So we require this 5 gates. Okay, so 5 XOR gate, 5 OR gates to implement this function A XOR B. Okay, so A XOR B, I think it is we are getting it here, A XOR B, and this being the A XOR B input, and this is our second output. Yes, no problem. So it is correct. So here we get A XOR B. You just verified from the this expression. So you'll find that this is A XOR B. So this is A XOR B, and if you further get this expression implemented, these inputs further we move. So we'll see that the output here we are getting is A XOR B XOR Cin, and the output which we get here is the same logic what we have done in the last slides. So using the same logic, we see that the output is this. So this is what the implementation of our this full adder using the NOR gates. Okay, then let's come to the subtractor. So subtractor is nothing but a circuit which performs subtraction of 2 bits. Okay, so half subtractor is A dash B. Okay, sorry, A minus B. Okay, again we will follow the same. So this is what the definition of a subtractor, half subtractor. So we have to follow the same procedure. So write the truth table, K-map, its function, implementation with this basic gates, NAND and NOR. So just pause the video and try the things by your own. Okay, so after doing that, you can verify the circuit, but first try it. Okay, so that is important. So you see half subtractor now. So half subtractor is, again you have done the black box, and here the output will be A dash A minus B. The inputs are A and B. For this, the outputs are D and B0. We have written as D and B0. So D is A minus B and B0 is something, some borrow will come. So that truth table for that will be can be written like this. So you see, when both the inputs are 0 0, difference, and we don't require any, the difference will be 0 and we don't require any borrow here in this case. Okay, but if the inputs are 0 and 1, so if one of the input is 1, then the difference will be 1. 1 minus 0 will be 1. Okay, sorry, yes, 1 minus 0, this case difference will be 1 and we don't require any BOR. But in this case, if we want to subtract 1 from 0, okay, 0 minus 1 we have to do, so then we will require some borrow. Okay, so some borrow will be there, so this borrow is becoming 1. Now if we borrow something, then this particular thing will become 1 0. Now 1 0 minus 1 the answer will be 1. So you see, that is why this is also becoming 1. So we have borrowed something in this case, we have to borrow in this case something, and again the difference is becoming 1. So this is the case. Okay, now when both the inputs are 1 1, then no problem, the difference will be 0 and we don't require any borrow. So here in this case the borrow will come in this particular case, okay, when the input is smaller than means the other bit which you have to subtract is greater than the other bit from which you have to subtract. So now to implement this, again we have to use our K-maps, and the expression which we get from our K-map implementation, we fill up these entries of the truth table into the K-map, and we find that the difference is A XOR B. Okay, so it is, no need to surprise, because this, the thing if you are getting is this expression. If you have tried it by your own and you are getting the same expression which you got for your sum expression, okay, implementing the half adder, then no problem, it is right. But the only difference is the difference in the borrow circuit. So earlier it was A dot B, but now the borrow circuit will be implemented by A complement B. And to implement A complement, what we do is we put a NOT gate here. So this is the expression for your half subtractor. Okay, so this is the circuit for your half subtractor. Now this same circuit you can implement with the help of NAND and NOR. No need to explain it. You can verify it writing the terms in the same order, following the same procedure which I have already told you, putting the bars and then implementing it with this circuit. You will find that this particular circuit, this 4 5 NAND gates will implement your difference and the borrow as well. Okay, so here you can see A and B are the inputs. So here if you will verify, your output will be A dot B bar and over bar, okay, over whole bar. Similarly here if you will identify, you will get this as the output, and then when you combine them together you get this is the difference and the borrow here as A dot B. So I have written all the outputs as well, so what you are going to get. Similarly for the NOR gate as well. Okay, so this is the implementation for your NOR gate. Okay, you take the inputs, you find the output here, so it will be A plus B whole bar for this, and then you can find the output here, find the outputs here. So this is, the method to find this circuit is just manipulation of the basic expression which you got. Okay, so this is what you have to do. Now let's come to the full subtractor. So full subtractor is a circuit which performs subtraction of 3 bits, okay, not 2 bits but 3 bits. So the circuit is a little different, but again it will be repetition of the half subtractor, but we have to follow the same procedure. So if it would have been a physical class, I would have asked all of you to do it, and I will just watch you how you do it, and if you have any problem, then only I interfere, else I don't interfere and I'll let you to do the things by your own. But being the online class, you just pause the video and try to do it by your own. Okay, because I am going to give you some tutorials based on this, and I will ask you to do it in the tutorial class also. Okay, so if you are not able to, if you don't practice it sufficiently, then you will not be able to implement any given circuit with the help of the verbal statement. So you try it by your own. Okay, so this is what the expression is. So I have given you the mathematical expression for this, A minus B minus C. Now you consider that there are 3 variables, and you identify the number of outputs and then write the truth table for it. Okay, with 3 inputs and the 2 outputs. The 2 outputs will be difference and borrow, and the 3 inputs will be A, B and C. So you see that how your truth table, what are the entries for your truth table. Okay, following the same logic which we have seen in our last slide for the half subtractor. Then once you get that, you fill those entries in the K-map, then simplify it with the help of your simplifying techniques, write the expression in SOP or POS form, implement it with the help of the basic gates, derived gates, NAND and NOR gates. Okay, so this is what you have to do. You try it by your own. So let's see the full subtractor. So the full subtractor, if I write, so these are the all the possible combination. So 3 variables, so there will be 3, there's 8 possible combinations. So we have returned the terms as A, B and B in, borrow input, okay, and the outputs as difference and borrow output. So you can see, so you see this, applying the same logic. So if all the inputs are 0, 0, then the difference and borrow both will be 0, okay. If one of these 0, 0 minus 1 is 0, 0, 1 is there, then you see 0 minus 0, 0, but 0 minus 1 we will require both, I mean the borrow will be 1 and the difference will also be 1, using the same logic which we have seen in our half subtractor case. Here again same logic, so both the outputs will be 1. Here the 0 minus 1, okay, so you see that 0 minus 1 will be, you have to borrow, so you have borrowed something, so then you have borrowed, so 1 0 minus 1, okay, so the borrow is this difference is 1, but 1 minus 1 is again 0, so that is why it is coming like that, okay. So you just write them, all of them, and then you see that the output, the difference and borrow both are becoming 1 in this particular few cases, whereas you get the outputs like this, okay. So here you can see, verify the any of this combinations, input combinations, and you will find that it is same as I have explained, okay. So it is correct, and then you can see this for the last as well. So 1 minus 1 will be 0, so 0 minus 1, so you will require, because 1 minus 1 will give you difference and borrow both 0, but then 0 minus 1 if you have to do, then you will require the difference and borrow both will be 1, okay, so both will become 1, so that is what is coming. Now the black box implementation, so we have to fill to get this inside this black box. So the black box will have 3 inputs and 2 outputs. So to get the circuit inside this black box, we have to implement, we have to implement it with the help of K-map. So first we have to fill this outputs in our K-map, and then we have to simplify it, that those K-maps, okay, for each of the output. So this is the K-map for our difference output, and this is the K-map for our borrow output, okay. So if we write them, then we can see, fill up the entries, and you see that your expressions are coming like this, okay. Fill up the entries. So you see that the entries are, let me check it whether I have written it correctly or not. So this is the expression for B0, so 0 1 2 3, okay, so this is your borrow and this is your difference, no problem. Now if you realize it, so then this is the function, okay. So if you want to implement it with the help of basic gates, then use this expression. If you have to simplify it with the help of derived gates, then use this. So this expression becomes more important for us because it will be used in the later circuits to implement our NAND and NOR implementations as well. So these are the expressions, and then with the help of these expressions you can implement it using the same logic which we have seen in case of full adder. We apply the same logic, and the only difference is this AND gate, okay. So this not gate. So if you just put a NOT gate here, okay, in one of the input, then it becomes your, okay, in one of the input, then it becomes your subtractor, full subtractor rather than a full adder. So in a full adder and a full subtractor, this NOT gate, these two NOT gates are just different, okay. Else the whole circuit is same, and you can realize, you can understand the circuit with the same logic which I have explained you earlier. Now full subtractor using NAND and NOR, again if you know that how you are getting this A XOR B with the help of NAND gate and NOR gate, you implement it, and then you apply these other inputs and you get the difference and borrow. So you verify this, whether this implementation is correct or not, by your own. So I have shown you these circuits, and the D0 and D and this difference and borrow, you will identify, I think that they will be correct, but if there is any mistake, you tell me it in the doubt class or the tutorial class. So this was all about this half adders and full adders. And now the last circuit of this today's class. So let's see, after this all, we want to implement a combined circuit which can perform both addition and subtraction, okay. So probably it is going to take some time, so I'll start I'll do that in the next class. So this is what about our today's class. We'll continue from here itself in the next class. So thank you to all for listening. Thank you.